Uh, I agree wholeheartedly with Alex. And as you'll see during the talk, there are serious implications, serious ramifications if we don't, as researchers in A-Life, but as researchers generally, if we don't tackle the external concerns. Basically, if we say that our responsibility stops at the technology and we're not interested in the ethics of what we're doing or the ecological implications of what we do as computer scientists, then we really risk making some not just big mistakes, but potentially catastrophic ones. And that's obviously something that I don't think is desirable. So this all came about because I do a lot of research monitoring insects, and that research involves putting small devices like Raspberry Pis and audio moths and other things out into field sites and farms. And it also involves machine learning running on, supercomputers in countries other than where I'm located that are potentially that are actually burning fossil fuels for their power. So I wondered at one point while I was, unable to sleep at night, thinking to myself, well, does it make sense for me to be doing deep learning in order to track an insect? And how much carbon am I pumping into the atmosphere just to track this single bee, whilst I think to myself, oh, I'm actually helping by understanding how these insects behave. And that kind of concern got me thinking about the fact that we need some kind of guidelines. And I started exploring this idea with some of my collaborators, Hazel, Parry, and James Cook, you can see here. And we put together this sort of brief introductory paper outlining some potential guidelines. Okay, so the question is then, well, if we're going to introduce these devices that use mechanical interventions in the ecosystem, they're often operated by electronics, what's the goal here? And clearly what we want to do is to better understand nature's ecosystems, to enable us to manage threats to all kinds of life forms, especially those that are under threat because of our own human activities. We also might want to be reducing human inequality, providing enhanced environmental conditions for us to live and to grow food. And that's the goal. But it's got to be more than just a goal. We've got to take into account what the potential ramifications or side effects of meeting these goals is. And that's where this project comes in. Now, this isn't some new thing that we've just started to do recently. So here we've got a picture of a oldie world scarecrow made out of kind of recyclable materials that are sourced locally, old clothes, a bit of wood, some hay maybe. It doesn't move or reproduce or do any of the things that an artificial life researcher would normally think of as being part of a living system. But I'm not just interested in the individual organism. I'm very much interested in ecosystems. And when you consider the dynamics of the ecosystem and the way it responds to something like what would otherwise seem to be, to an A-Life researcher, a static, passive object like this humanoid form, it's not so clear to me that there's an important distinction here as an A-Life researcher that I need to draw to say, well, this is not within the realm of my interest. So just to, kind of push the case a little bit further, this is just taken from the website of a local hardware store. You've probably seen these things around. It's a contemporary scarecrow, you could say. It's got a passive infrared sensor, so it's able to actually detect when birds are around. And it does pretty much the same thing as the old scarecrows, but the intention of having it respond to its environment is that it's able to overcome the habituation of birds to a scarecrow, supposedly. Now, in fact, these things don't work very well. But let's just say for a minute that it did work well and that it effectively scared birds from your backyard for $36.49. if it's doing that, of course, we've got to consider, well, what do the birds do? And what they do is they just move next door, right? So you might have shooed them away from your own back garden, but they're going to go next door and change their foraging location. So what you do impacts your neighbor. Now, on top of that, birds also have like useful non-pest related activities. So for instance, they'll eat spiders, and they'll also eat the caterpillars that are simultaneously destroying your crops while the birds might, right? So by shooing them away, you're actually providing safe haven in your garden for caterpillars, which are another pest that you then would have to control. And what would you do for that? Well, maybe some people would say, well, you just spray chemicals on the garden to keep away the caterpillars, right? And you can see this kind of cascades occurring even within a simple back garden. Now, a device like this is obviously manufactured usually in Asia, maybe under undesirable kind of working conditions for the people in the factories. It's built from non-biodegradable materials. It's not recyclable. It contains toxic chemicals. And once it's finished its useful life, which is not very long, it ends up in landfill, often landfill in somebody else's country. So it becomes someone else's problem. And this moving of our local problems from our back garden to our neighbour's back garden, or from our country to another country where the device was manufactured under poor conditions, that materials were extracted under poor conditions, and it's disposed of as e-waste under poor conditions, is not really where I think we should be going. So whilst it's true that this kind of device that I sort of shorthand call an emu, after the Australian bird, flightless bird of the same name, but also a Mechatronic ecosystem management and monitoring unit, it can improve the way we manage and understand agricultural and natural ecosystems, because we can use it to monitor and potentially to mitigate against some of the issues that might arise under degraded ecosystems. So it can be beneficial. But if we do a bad job of things, then it can also undermine our efforts to conserve nature. It can disrupt ecosystems, damage habitat, and as it said here, in the ultimate, extreme, it can drive people into poverty by ruining the natural systems on which they've depended, maybe for generations in some cases, for food and production of food that they might sell. Okay, so we're not just talking about scarecrows here. Here's a few examples of more sophisticated ecosystem management and monitoring units. Robo Bees are one of my particular pet hates. They're micro unmanned aerial vehicles that are intended to replace bees for crop pollination. I'll go into a little bit of detail about those in just a second. Starfish destroyers have been deployed on the Great Barrier Reef in Australia, and they've got lethal injections, and they target the crown of thorns starfish, which is an invasive starfish that destroys coral on the reefs en masse and is proving to be quite a major problem. Quad Eye is from Norway. It's a machine learning and computer vision system through which salmon, as they swim upstream to breed, have to pass. And it records their body patternation from 4 different sides, decides whether or not they are escaped farm salmon or wild salmon, and diverts them accordingly to prevent the wild salmon from breeding with escaped farm salmon. Tags are also identified on the salmon. Here's some others. So intelligent scarecrow over on the left here, this one's actually for elephants. But once again, the idea is the same as the owl, basically. It senses the presence of the animal that it's supposed to frighten, using sometimes quite sophisticated techniques in data analysis or machine vision. And it then can learn to respond to what it perceives in such a way as that the animal doesn't become habituated to its presence, and it continues to maintain a frightening presence for the animal. So obviously, if you've got elephants trampling through your villages and your farms, that's quite damaging. And likewise, we've got the same issue with birds. In tracking insects, you can place all kinds of different tags and wearable devices on their bodies. Here's something from a collaborator of mine at CSIRO. It's an RFID tag that's placed on the back of a bee and enables you to determine when the bee meets the reader, which you place at different locations around the field. Acoustic monitors and camera traps are another very familiar device that's often placed in natural ecosystems for monitoring the presence of animals. So that's really just a selection. Each of them has its own benefits and potential problems. Robo Bees I've written about quite extensively. So here's a little bit of detail on these. Firstly, they're problematic from a numbers perspective, right? So just talking about managed honeybees, not wild bees, not wild honeybees, not the 20,000 species of bee in the world, just managed honeybees. For a particular season, it was estimated in 2016 you would need 16 trillion of them just to pollinate the crops, human crops. So that's not talking about wildflowers or anything else. That's only the number of robo bees you'd need for the crops, right? So it's an enormous amount. They cost money to make. They're not free, unlike kind of wild bees. So 75% of the world's farms, basically, which don't fall into the kind of industrial Western developed style, would probably miss out on pollination in this case if we were to depend entirely on robo bees. As I mentioned, for many devices, they're manufactured from environmentally damaging materials that have to be mined or extracted or manufactured in other ways. When they're finished with, typically they're not biodegradable or recyclable. And often if they're damaged in the field, they'll just be left as litter and be very, very difficult to retrieve. They're quite small, these things, about this big. So you can imagine if these things fly off into the forest under, misguidance, they're not going to be found. And then they'll be sitting out there waiting for an animal that might think of them as an insect to eat them. A lizard comes along and finds a poorly flapping ornithopter robo bee on the ground, it's quite likely that it'll try and eat it. It's evolved to try and eat things that look like insects. And of course that would be fatal. As it would be if, potentially anyway, if a crop duster aircraft were to strike one of these and ingest it into its engine. So that's the kind of physical problems with these devices. But worse than that, they're agriculturally naive in the sense that they actively displace the pollinators that we're trying to support. So basically they worsen the situation with respect to our dependence on natural pollinators by outcompeting them on the crops that we've planted that are displacing the wildflowers that the native bees would originally have fed on. So there's a big problem there. Now, because these devices will need to be trained and developed to pollinate flowers that are economically valuable to humans, that means they're going to pollinate the crops. But economically, there's no reason why people would invest billions of dollars in building robo bees that across the globe would pollinate our wild ecosystems. Now, apart from the fact that these robo bees don't fit within the ecosystem, they can't be eaten by other animals. They're not going to be capable of traveling the kinds of distances. They're not reproducing themselves. So they're just ineffective in natural ecosystems. By outcompeting the wild pollinators and not pollinating wildflowers themselves, they're guaranteeing the kind of the doom of native terrestrial ecosystems that depend on insect pollination. And that's just about all of them, to be honest. Not all, but nearly all. So we need some guidelines. There are some sample guidelines that we can use as a starting point when we look at the introduction of invasive species. Here you can see a cane toad, which was introduced in Australia a bit more than 100 years ago, as a way to, or about 100 years ago, I think, as a way to handle the cane beetle. Turned out to be completely ineffective at doing that. And now these cane toads are destroying Northern Australian ecosystems. So we're not very good at introducing this kind of biological thing. Technology is going to make things even more complicated. And we've also got to consider not just the kind of ecological consequences, but the cultural and social consequences. So in a nutshell, then, I came up with these 7 guidelines for introducing emus. Now, you can have a look at these. I'm not going to read them right now through. And you probably say, look, most of these are really obvious. Okay, there's nothing here that would surprise people, I think. But in practice, these are very difficult to implement. They conflict with one another under some circumstances. There might not be funding allocated to particular components here because it's not sexy enough or it's not considered a high enough priority. But if we don't look at all of these aspects of our introduction of electronics and robotics to ecosystems, we risk doing some serious damage. And you can read some of the reasons that I suggest these issues are hard to handle in the little post-it notes on the screen there. So I'm just going to quickly fly through a few of them. This one about providing greater global benefit than damage. This comes back to what I was saying before about doing deep learning in one side of the world in order to track a single honeybee on the other side of the world. It's a very hard balance to make. Like, how much do you really learn by doing this? Is it worth it? And what's the cost? In order to kind of allow us to begin to understand whether or not these costs outweigh the benefits, we've really got to have clarity of purpose. We've got to know what is our goal, and we've got to say, is that goal significant enough that it warrants the means by which we get there? We've got to look beyond what we as engineers or computer scientists do, and we've got to consider, you know, the social and the ecological consequences of our activities. We can't just do stuff because we as engineers or computer scientists think it's cool. And to demonstrate the difficulty of this, really, here's a real ecosystem map taken from the literature online. Basically, when something comes up as your target, you can see I've kind of circled a bee over here as being the target of some particular device. It might be also that that device interferes with or influences the behavior, even subtly, of other species, but they might not be other insects. They could be plants or aquatic wildlife under some circumstances. And those kinds of interactions can happen throughout the life cycle of the device, but also by influencing the behavior of your target species. Anything that interacts with that target species is also potentially indirectly influenced, and that can be a very significant change to an ecosystem. So we've got to look at how matter, energy, and information are exchanged amongst the components of the ecosystem, both the biotic ones and the abiotic ones, in order to assess really what the implications of introducing our device are. And that's a big ask. I'm not saying that's easy to do, but if we're to avoid making, you know, a big mess, it's the kind of thing we have to set aside time and resources for. Now, when I say, you know, we've got this device and we introduce it to the ecosystem, often it will just sit there and it will remain there indefinitely. As I mentioned before, one reason for that is that the project just kind of runs out of money and nobody's got the resources to remove the device from the ecosystem. Now, a simple camera trap, you might want to go in and collect because it's a valuable commodity and you might need the data on the camera trap. And the only way to extract it may be to go and take it out physically. But for instance, for security, camera traps might be concreted in place. And that might be just too difficult to remove after you've done it. So you may leave this concrete thing here in a post, you know, a post in a concrete base and walk away with your valuable data, leaving the rest in the ecosystem. Some devices decay, as you can see here, into microplastics that can be damaging, and e-waste, as you no doubt realise, is already a dangerous problem around the world. We don't want this stuff littering our ecosystems, especially if we're trying to help them. Other interactions, of course, we need to consider are with the stakeholders and the communities that earn a living from the ecosystems that we're working with. We need to consult with them directly. They're going to be the experts and they're going to have insights that we as computer scientists or A-Life researchers might not have. We've really got to pay attention to them. And likewise, you know, whoops, trying to get this thing to work. Likewise, we've got to consider the cultural and aesthetic values of the landscapes with which we interact. And, there's plenty of articles, as the two here demonstrate, on how drones interfere with our experience of landscapes and wilderness. But likewise, camera traps and other devices set up can do maybe quite not so intrusively, but similar things. Finally, the final one of these guidelines is to intentionally harm organisms only as a last resort. Now, most of us don't think twice about swatting a mosquito, but mosquitoes too are part of food chains. And whilst they certainly cause an untold amount of damage to human lives through the diseases that they spread and just the general nuisance that they are, we need at least to consider that and the benefit that mosquitoes play. Now, we might decide that the benefits that they play in particular ecosystemic situations are not significant enough that we should avoid eliminating them or breeding mosquitoes, at least, that don't spread disease. So I'm not saying don't kill mosquitoes, I'm just saying consider what the costs are and make an explicit allowance for that in your thinking. So once again, there's the guidelines. I won't go through them again. You can actually read them in the article yourself. Thanks for your time and happy to answer questions.